Yeah, so I joined this meetup last week. It was really exciting and it was great meeting you all. And today I would like to show a bit of my work. It is not directly in quantum computing, so please let me know if I'm too fast, too slow, if it's interesting or not, and then I hope to make it a nice meetup with you all. It will be about atom by atom designing and realizing electronic quantum matter. And the whole motivation is that novel materials basically drive new technology. Where would we be without semiconductors, without silicon technology? Not here right now, that we can be sure about. Meanwhile, also superconductors became extremely important, MRI, but also for all new developments at IBM, Google, and other quantum computing companies. We wouldn't be there without superconductors. And to know how they work and to design improvements, we need to understand them physically. We need to understand their band structure, roughly indicated here in the bottom. So basically the energy diagram of the electrons. And those look very different for different types of materials. And with some we are very familiar, but others we would like to only invent from now. And for that purpose, we would basically like to simulate quantum mechanics to unravel new phenomena. For example, high temperature superconductivity, we even don't understand it yet. And to create a material that shows high temperature superconductivity, it will be best if we understand it first, and then we can engineer it in a targeted way. So how to simulate it? The system size, if that is n, it grows exponentially, and for classical computers it will be hard. The universal quantum computers are not, not there yet. So I will discuss a stage in between analog quantum simulation, where we basically use a controllable quantum system to study another less accessible or controllable or non-existent quantum system. And that basically means that from theory, we have a model Hamiltonian. It can be non-interacting or interacting electrons. And then in our analog quantum simulator, we have an experiment where we realize this Hamiltonian, we measure to verify if it's really the case, and then we can modify it, measure again, etc. Please interrupt with any questions if you want. This is based on the idea of Richard Feynman. In his lecture, there is plenty of room at the bottom where he envisioned that we could just put atoms in the spots that we want and create molecules or materials by ourselves. And since 20 years, this has really been realized using ultra-cold atoms in optical lattices, same technology as used for quantum computers, trapped ions, photonic lattices. I would like to discuss another approach, which is not very well known or very well established yet, and that is electronic lattices. Very important, as most technology in the world is still based on electronics. This is a preview of my experiments. So these are images of what I measured. And these represent the following Hamiltonians, these lattices. And they are all realized in a scanning tunneling microscope. Some of you might be familiar with it, some not. So basically in an STM, we have a very sharp tip, one atom at the apex. And with that tip, we come close to a conducting surface. And thus we can measure measure a tunneling current. So we have quantum tunneling between that material and our tip, as we are very close. And the tunneling current behaves exponentially with the distance. So it means we are extremely sensitive to that distance. Then if we bring that tip even closer, we can also move atoms around on the surface. Atom manipulation, shown first in an IBM lab with xenon atoms on a nickel 111 surface. And then you already see we are already getting there where we can create, basically certain shapes and materials atom by atom, and then we need to measure it. And that can also be done in an STM. because the derivative of this tunneling current is proportional to the density of states of the material, and that basically represents the band structure that we want to know. So yeah, we can get all information from it if we do that measurement. My lab looks like this. I can show a virtual lab tour, but we can also do it at the end because we need to stop the recording for it. So maybe at the end. We work at low temperature, 4 Kelvin, or here even 10 millikelvin. You see, I think for most of you, familiar picture of a dilution refrigerator. Here we can apply magnetic fields up to 15 Tesla, energy resolution better than 8 microelectron volts. So this is all in my lab at NIST, where I work with great people under the guidance of Joseph Stroscio. Much of the work that I will present now is also carried out at Utrecht University in the Netherlands, and there with Ingmar Swart, and there we worked at 4 Kelvin. Okay, I will skip the lecture for now because we need to stop the recording. But first, more about the analog simulation. So to create model Hamiltonians, we basically want to create artificial atoms. And we just discussed that we can use an STM to manipulate real atoms in certain spots. And here you see on the left, if we move, in this case, iron atoms on a surface in a coral, then you see kind of a standing wave here, and a standing wave of electrons of the copper surface underneath. And this looks kind of like orbitals of an atom. So you can interpret this as orbitals of a 2D atom, and this would be an artificial atom created by these real atoms that scatter the electrons underneath. And here you see it a bit better. So these black ones are the scatterers again. These are CO molecules, and they confine the electrons here. At low energy, it's like a 1s orbital. Higher energy, like a 2s orbit, 1p orbital, and here 2s. So that is great. We created artificial atoms in this way. And if we have an atom, we can of course also make a molecule or a lattice. And that you see here, this was carried out at Stanford, where all these black things are again CO molecules, and they confine the electrons of the copper 1,1 surface underneath into this honeycomb shape. And then they measured it and saw that it looked like graphene, as expected based on this shape. So now we come to my work, where we want to manipulate also artificial atoms in shapes that don't exist in nature. And one of those shapes is a leap lattice. Really interesting because cuprates, one of the most important types of high temperature superconductors, the planes of those consist of those square-like lattices that are called leap lattice. You see here these copper oxide planes. But in 2D, it doesn't exist. So from theory, we know what it should look like, but we don't know experimentally. And that should, of course, be established. So why do we think this is interesting? If we look into the band structure again, we see that the purple, I don't know how familiar you are with these kind of things, but purple looks a bit like graphene. And the red part is a flat band, and flat bands are extremely important. It basically means that the electrons have no kinetic energy, but that they can interact very well. And interactions is what is needed to create superconductivity or other interesting phenomena. For superconductivity, two electrons need to interact such that they form a Cooper pair, and that is the basis for superconductivity. So we are looking for those flat bands, and we want to know if they really exist in such leap lattices. So in our measurement, it's supposed to look like this. We basically, the flatter it is, we see a higher peak. And we expect when we build this, when we measure on such a red side, that we see a strong peak in the middle, And when we measure on the blue side, that we see 2 side peaks. That will be our signature of this lattice, if it worked out to create it. So let's try. We want to have the electrons on these sides. So we need to build a structure around them to confine them there. Oh. So that would look like this. We can put carbon monoxide molecules there on a copper 111 surface, which has the electrons nicely at the surface again. And now we expect to confine the electrons here on the red and blue sides. And then in reality, it looks like this after a lot of work to move these CO molecules one by one. Of course, we automated it afterwards. Yeah, and so this would be the basis for our analog quantum simulation. And now we think we realized it. So now we measure, and measurement on this red spot. Hey, we indeed see a strong peak in the middle, as we expected for this flat band. And then we measure in the blue spot, and we see 2 side peaks, as we hope, based on what we think in theory. So this is great, and we can look in spatially. So now in our scanning tunneling microscope, after we moved all these CO molecules in place, we are scanning this material here at a constant height to see if we have more electron density or less. And we see that it's very different for this flat band here. And we see that it is entirely localized on the red spots. And then for the side, for the peaks next to them, the graphene-like Dirac cone are in the other spots. And this is the perfect signature of the leap lattice, establishing that we indeed build it. I want to show one other brief example. Let me check the time. Okay, already talking 10 minutes. Because something else that doesn't exist in nature in a well-determined way is a geometric fractal. Fractals actually exist everywhere in nature. It is basically everything that repeats itself at every length scale. For example, this Romanesco broccoli, which is like a pyramid of many small pyramids. Trees also, big branching into smaller ones, etc. Yeah, I really love it. So I have many examples. But even our own respiratory and circulatory system, our brain, it all consists of fractals, which are branching into smaller and smaller parts, where we basically have a relatively small volume compared to a very big surface. And something that not everyone is aware of is that the dimension of such, oh, I have some problem here. Okay, of such systems is very interesting because it is not 3D, 2D, or 1D, but something in between. And one can explain that as follows. In 2D, here, if we multiply the base by 2, we basically need 4 blocks to fill it out. So exponent 2, that is our dimension. It works the same in 3D, 2 to the power 3 gives 8. Here in this Sierpinski triangle, a triangle consisting of smaller triangles, signature of the fractal. As we left out the middle, then to multiply the base length by 2, we only need 3 pieces. And that gives as an exponent log 3 over log 2, so 1.58 basically. And we also built this system in a scanning tunneling microscope. You see here, copper 111 surface in the back, CO molecules confining the electrons in between. Here to show you, it's really a fractal with a big triangle consisting of smaller triangles, consisting of smaller ones. And then we also did measurements on this, and we could establish that it actually had this dimension around 1.6. I won't give you the details now of how that was determined. As a conclusion about this, is that we realized a highly tunable platform, an electronic analog quantum simulator using carbon monoxide molecules on copper 111. We discussed a Lieb lattice with a flat band, which could be very interesting for superconductivity. We discussed a fractal, and we also built several more structures in the lab. What I haven't discussed is if we saw superconductivity there, right? We created a material in which one would expect it, but we didn't see it yet. And that is because in this material, there is so much screening of the electrons because of the bulk. We use the copper system because of the bulk underneath, that we don't have strong electron-electron interactions. And now the field is moving to new manipulation platforms. For example, here you see 2 layers of graphene on top of each other, also creating a certain potential landscape. Instead of using these atoms, they used basically the Marlou pattern of 2 graphene layers to create a potential landscape and thus artificial atoms. And there actually flat bands were found with interactions and with superconductivity. So that is extremely interesting. And then one more outlook that we can't miss out on in this group is, can we actually build a quantum computer based on atom manipulation? And the great group that focuses on this is the group at the University of New South Wales in Australia, I'm sorry, of Michelle Simmons, where they use phosphorus donors in silicon as electron spin qubits. And now you might understand the principle really well, because they have a similar microscope. I had copper in it, but they have silicon in it, and it is passivated with hydrogen. Now they use the same STM tip, applying some voltage to it to desorb the hydrogens. So basically this is a great atom patterning step, atomic precision, to determine where they want to take out the hydrogens. And then they dose phosphine gas, and that will sit exactly where they took out the hydrogens. So extremely well determined. They heat it, so the phosphorus is incorporated into the lattice, and then they can cover it again with silicon. And these qubits have a nice long coherence time, and it is all extremely well defined. So I think they aim for a quantum computer with 10 qubits in a year. I am not sure about that. So it is really in progress, but it could be very promising. And I would like to discuss one more topic after this. But yeah, this was my group in Utrecht, and now here at NIST. And I would like to tell something about a quantum program we are organizing now, but but maybe first to finish this, I am very curious for your questions.
Yeah, this is pretty awesome here because it covers lots of chemistry. I've used SEM before, electron microscopy. I'm just curious, with the colors, like the diagrams and the circles, do they come out that way, or is that like adjusted for visual appearance?
You mean here, right? For example, or
further back.
Yes, yeah, that is adjusted. You mean this one?
Like this one.
Yeah. This would basically our measurement is just an array of values, and then we can display it any way we want to visualize nicely. And this just displays that here the atoms are higher. Yeah, we basically measure electrons with electrons in this case, because our sharp tip, yeah, electrons, and then we measure the atoms underneath, or basically the electrons of those. And there, where there are many electrons, we can tunnel well, and we have a high probability, which you see here as high.
And then as far as like the molecules, I see carbon monoxide, iron, copper, I think calcium and oxygen. Obviously, some of these are oxidizable with the iron and the copper. Has it just been established over time that these are the ones that work?
Yeah, in this case, so it really depends on the purpose. In this case, it's pretty simple. We have this copper surface, which has a nice, we call it 2D electron gas. So electrons basically in 2D at the surface, and we want to use the atoms as scatterers for them to create this kind of standing wave, which is orbital-like. And we can use many for those. Iron works, here carbon monoxide molecules work. It is just important that they scatter and that we can move them around with the tip, that they don't just stick to the tip or stick to the surface. So that is trial and error with some help of calculations, density functional theory, for example.
Very cool. Does anybody have questions for Marlou right now?
Absolutely. You have shown two different electron microscope systems, yours and the one in Australia. It seemed to me that the one in Australia is based on almost like an EDM process where you're using the electron beam to convince hydrogen atoms to leave, or it's sort of like a milling operation. You make them go away. And if I'm correct, in your lab, you're doing the opposite. You're doing almost atomic deposition. You're somehow dropping. So my question in your lab is, what is the source of your atoms that you are depositing on that surface? And so I'll let you talk about that, and then I have a question about your lattices.
Yeah, very good question. In this case, where we use carbon monoxide molecules on a copper surface, there so one important thing, these scanning tunneling microscopes, it is all in vacuum. Otherwise, we wouldn't be able to measure atoms because the air consists all of atoms and molecules. So we are in ultra high vacuum, and it is very cold, as we discussed. So here we just dose some carbon monoxide gas into that vacuum. And some of it will land on that cold surface, and because it's cold, it will stick. And that means we will have molecules basically scattered around on the surface, and we use our STM tip as a kind of broom to create these shapes.
So it's like dusting it with a handful of sand, and then you're using the electron microscope as your finger to draw patterns in it.
Basically, yes.
Wonderful.
Yeah, a very sharp finger, and that means that we can actually do it.
Okay. My question about your electron lattices, you were talking about these two-dimensional atomic lattices that are hopefully in search of high temperature superconducting materials. Am I correct? And
yeah, correct.
My question would be, you showed a couple. You showed where the wells of electrons would exist. What would be the patterns of flow of the electrons through the matrix? Does it stay in the two-dimensional matrix? Does it are the electrons ejected from it at any point?
They are ejected. So
like this one, or actually you had some electron microscope pictures of it. I mean, but So the idea of the this one, where the electrons are they moving around the lattice?
They are not around, but indeed we could use two types of techniques to measure this. In this case, we are the electrons are basically stationary.
They're trapped.
Yes, they are trapped, and in this case, they are even strongly trapped because this flat band with the high, what we call density of states, actually. And it's quite narrow. It means that they are very localized here. So here they are really trapped, and we measure it with we go over with our STM tip, and then actually a process happens. A bias voltage is applied between sample and tip, and then the electrons will tunnel from the sample to the tip, or the other way around. And that is our measurement principle. Mm-hmm. So they will move between those, but basically from those localized spots. We could also do transport measurements on well, not on this specific system, but if we would create it in a clean room, and then one would need to create contacts, and then one would actually apply voltage and have a current go through. And then we actually expect that it would conduct well here in these blue peaks, but not in the red one, despite having many electrons here. But as they are trapped and localized, we expect that it won't conduct well.
Oh, okay. So when you were mentioning conductivity, if you were would you be trying to conduct electrons like from left to right or top to bottom through the two-dimensional plane? Or I guess that was what I was wondering about. So but you're telling me that the electrons are they're kind of trapped in those wells. So the superconductivity would have to be related to like it's the energy state of each electron is, or the frequency it's oscillating at or spinning at or whatever. Okay. Very good.
One. Yeah.
I have a question. You mentioned earlier that there was a German lab that had had some good results. What was that German organization that had the good results?
Yes, maybe let me. So that is at the University of Hamburg. So this principle is not only used to create band structures for new materials like semiconductors or metals, etc. But also, for example, to have spin chains. So atoms with a certain spin, and one looks at the interaction between them. And this is also used, these atomic chains can also be used, for example, to try to find Majorana fermions, which could be a great ingredient for quantum computing. And this lab in Germany, at the University of Hamburg, Wiesendanger's lab, they have done that recently. So they used exactly the principle that we just discussed, STM tip and moving atoms one by one to create a chain of magnetic atoms. I can look it up for you now. Seeing Majoranas. Here we go, precursors of Majorana modes. Yeah, maybe this is kind of part of the news, right, Kevin?
Very technical. Let's see here.
Yeah, this is manganese atoms on on a niobium surface. You need a superconducting surface for it.
And I do have some things to feature, and we can come back to that video after kind of like the feature, the headlines kind of stuff.